Let me first welcome everybody to this webinar that is hosted by the GRSS IEEE GRSS Turkey chapter. We are very happy to and honored to be hosting Dr. Daya Sagar for this 2 days webinar. Dr. Daya Sagar is an distinguished lecturer of IEEE GRSS, a professor at the Indian Statistical Institute. He's a member of New York Academy of Sciences, a fellow of Royal Geographical Society, a senior member of IEEE GRSS, a fellow of Indian Geophysical Union, and so on and so forth. He has also recently authored a book on the topics of this lecture, more or less. It's titled Mathematical Morphology and Geomorphology and GIS-CI. And this webinar, it will involve two back-to-back lectures on mathematical morphology. The first topic will be mathematical morphology in geoscience, remote sensing, and geospatial data science, and it will be an overview. The second lecture will be titled Processing and Analysis of Digital Elevation Models via Binary and Grayscale Granulometries, Morphological Interpolations, and Morphological Distances. Now, today's webinar is organized in two parts. So we'll have a 45-minute first lecture, followed by a 15-minute time period for any questions that you may have that you are willing to ask. And if you ask during the lecture itself via the chat, I will be happy to ask your questions in the time periods allocated for the question and answers. Then we'll have the second lecture again for 45 minutes, and then we'll have another 15 minutes for questions and answers. I think we can begin now. Another announcement I should have is a slight apology about the time scales. There was a mix-up. The webinar was first allocated to start at this time. Then there was a mix-up with the announced time dates, and then it was reset and so forth. So apologizes if you had any problems. But anyway, I think we should be okay in either case. Dr. Sagar is, I think, ready to begin his talk, and I'm happy to give the stage to him. I'll be stopping my screen share. Dr. Sagar, if you're ready, we'll be happy to hear from you. Thanks.
First of all, let me thank Turkey GRSS chapter, and as I mentioned to my good colleagues and Dr. Ertruk and then Dr. Taskin, that this is the first ever GRSS talk that I got the opportunity to talk, and just after I was appointed as a GRSS DL in July this year. And then as they have introduced that there are two topics, and the first topic is on a kind of, the overview, illustrative overview on how mathematical morphology, which is a kind of mathematics to study the shapes and functions. In fact, that particular topic is mathematical morphology is more of European, it's more popular in Europe, and but of late we have started employing mathematical morphology, and then we have a group that where we employ a lot of geoscience related applications that we have shown through mathematical morphology. And as Dr. Ertruk has mentioned, there are two topics, and the first one is more on the mathematical morphology, and it's illustrative overview on not just in geoscience, remote sensing, and geospatial data sciences, and wherever you see the spatial data and how mathematical morphology can be employed to unravel very unique geometric, morphologic and topologic information that is actually hidden to our naked eyes, and how we can actually employ mathematical morphology to handle information retrieval and information analysis and quantitative characterization of information that we derive from spatial data, and then quantitative reasoning and modeling and simulation and visualizations. And I could see that this particular mathematical field could offer a number of operations and transformations, and to study all these aspects, I would say that they are all the basic ingredients of spatial data science. And The second part and first part, they have actually a kind of overlaps, but in the second part, I would like to emphasize more on how digital elevation model, an important source data for geoscientists, can be used by applying mathematical morphology. What is that we can do? And I would see that digital elevation models is a kind of physical system. And those who have actually missed this particular first talk, and they don't face any problem understanding the second talk, because as I mentioned, there is a kind of overlap. And now I would actually like to share the screen, and I would like, you can ask me in between if you want to ask a question. You can stop me, and if that is not there in the slides, and probably I will use the board behind, and which is quite visible. Um, I think this is. I think it's taking a bit time. I would prefer to probably share this. Yeah, so this is about the first topic, and you can see that mathematical morphology in geosciences, remote sensing, and geospatial data sciences, an overview. And on geosciences, I'll show just a couple of cases, and particularly how to quantify the roughness of the terrestrial surface, how we have employed mathematical morphology to actually define mathematical morphology. It is about the mathematics for studying the shapes and functions. And we have complete mathematical basis in this particular field of mathematical morphology, which is very popular in mining engineering and geosciences and pure mathematics, and even in computer science. And so of late, mathematical morphology has been employed in remote sensing image classifications, particularly hyperspectral images, and how they have been classified and mapped very important features by applying mathematical morphological tools, namely morphological profiles. If you are familiar with the group of the John Bendixson, Brujon, and Jocelyn Chonsett, and they have heavily used mathematical morphology, but with a slightly different names like morphological profiles and extended morphological profiles. And those examples, I'll just show a couple of slides. And then there are many slides on geospatial data sciences. As I mentioned, whenever you see spatial data, whether it is demographic data or simple geoscience data, or econometric data, which is shown in a map form, and this mathematical morphology has a big role to play to deal with all kinds of spatial data. So as I mentioned, this lecture is to make you aware of the field that is more European, and we employed this particular mathematical morphology in number of various different spatial data, and namely most prominent one is digital elevation model. My second topic emphasizes more on digital elevation models, and of course how mathematical morphology can treat DEMs. See, other data being demographic, economics, and environmental relevance. And I always used to talk to my students telling that in spatial data science, the most important ingredients are information retrieval, analysis, reasoning, information modeling, simulation, and information visualization. Finally, can we really develop a kind of model which would predict the behavioral pattern of the specific phenomenon of process of our interest? So that is where we have to really head. And then is there a single mathematical field that can address these basic ingredients of spatial data science? And I felt that mathematical morphology is one of the best approaches one can really handle. And as this was the slogan mentioned in my IGAS 2020 tutorial, And mathematical morphology is an area of geoscience that most people don't realize will literally change the way they look at Earth. And I would show you and I would give a brief a glimpse of it, and then you'll realize that it would be great. And if you people can really venture into this field of mathematics to take it to the next level, particularly in application domains. So any dynamical system requires a spatiotemporal model, requires information retrieval, analysis, reasoning, and modeling. And so if someone asks me in one single slide, I have to explain what all that I'm going to talk in the coming 2 hours is, can we really simulate a kind of terrestrial surface by following some fractal ideas and mathematical morphology? There is a way. And if you look at this particular data, it has a lot of geometric, morphologic, and topologic information. We know that there is some hidden information, but how to unravel that is a real big challenge. And the most prominent features are unique topological networks and valley and ridge connectivity networks on a terrestrial surface, and how we handle that, and how mathematical morphology has given elegant solutions. And can we really partition that terrestrial surface into watersheds in a hierarchical manner? And there is a way to do that. And that is one aspect. And then how to generate the artificial landscapes. And if we know the rule of how a terrestrial surface has been formed by following certain, nonlinear process, tectonic activity and endogenic activity, mostly from the weather conditions. If we can really create a rule to generate that kind of terrestrial surface, and there is a way to simulate the landscapes, and then, and to give another example here, and if there is a set of water bodies which were extracted from remotely sensed data, and if someone asks you which is that water body located at the strategic location, and specifically we use morphological distances to find out a spatially optimized solution to detect that particular water body which is at the strategic location. It doesn't just end there. And so if we have a number of states in a country, and I would call entire country as a kind of spatial system, and then the number of states are like the political units. And if someone asks you which is that particular state located at the strategic location, and obviously we will tell that in a descriptive way, a centrally located state. But can we really quantify that process of spatial optimization process? And we have a way to do that. And then how to actually use certain distances and location significance of the state in a process to try getting which are those two states are well connected and well interacting, and in terms of trade, and that is specifically from probably spatial economic aspects. And so that would come here. And there is other computational geometry problem, you can see it here. And most of our maps would talk about aerial area projection maps, and whatever the variable that we talk on the maps that we see in day-to-day life are all the political units, and then the geographic coverage, aerial extent of each political unit. But if I say that there is a kind of variable, a kind of a crime rate in each state, and if a smaller state in terms of area extent having a high crime rate, and we have to somehow show that particular state, though geographically it is smaller in size, should be shown in a much bigger way. And so that is actually, if somebody is a the cartographer, digital cartography person in the audience, and they'll understand how to generate variable specific cartograms. And we have a way to we have given an algorithm, and which is more of a computational geometry based algorithm using mathematical morphology. That is one aspect. And then, and how to partition the given data. And we use mostly in remotely sensed studies and geosciences, we follow many commercial softwares to partition the data into watersheds. But within watershed, what is the roughness value? And is there a way to compute that? And how that can be computed? We have some certain techniques called granulometries from mathematical morphology. And those techniques, you can upgrade those techniques to compute the roughness. It is not just the global roughness value. you can also compute the directional roughness values, and in a number of different directions, what is the roughness value, how it is linked to the process. That would also be covered, if not in the present talk and in the next talk. And then how to interpolate between the two landscapes. And I would say this is the source image and this is the target image. Can I make this source image slowly into a target image? And we require certain interpolations, and the most popular interpolations are linear interpolations, but mathematical morphology offers nonlinear interpolation studies. And within a large database containing a large number of images, and if someone asks you to compute which are those images are close to each other, what is the best pair and what is the best, worst pair, and can you really order those images by computing certain ranks for the pairs of the images, all possible pairs in a database. So this is what you are going to see in the subsequent slides. And so before I forget, and these are the two founders, these are Frenchmen, and Professor Georges Matheron and Professor Jean Serra. They are actually pure mathematicians, and also they are, the geoscientists, and the mathematics that they have invented or founded, that is mathematical morphology and geostatistics, were heavily applied in not only in geosciences, in other engineering fields. So this is the overview. This is spatial data, geoscience, remote sensing, geospatial data science, and very basics of mathematical morphology. And I don't give too many details on mathematical morphology because I would cover in detail in the next talk. And then mathematical morphology in geosciences, remote sensing, and geospatial data sciences. And so in geosciences, most prominent topic of research earlier was, Ridge Valley network extraction. And we have certain problems when we use the commercial softwares to extract the valley networks. And if it is highly hilly terrain, it would give very quickly the result and very appealing results. But if the terrain is rather less undulated, like in tidal regions, and many of those commercial software packages would fail to give the actual networks on the tidal flats. And that is where one has to take the curvature into consideration, and then morphology can be really used there. And then roughness characterization. And as I mentioned, the granulometric index would actually quantify the roughness of the terrestrial surfaces. And watersheds, and how do we partition watersheds? And from the watersheds, depending on their sizes and shapes, and then other aerial parameters such as what is the longest axis and shortest axis and perimeter and area of the watershed, we can derive power laws to find out whether they really follow the universal scaling constants. So that is where, and the most of the fractal, if you are familiar with fractal geometry, it would give you certain measures which are scale invariant. But those measures are just scale invariant. But what we want is the measure that is scale invariant but shape dependent. The moment we change the rule to investigate the function or a simple shape, the rule is actually a kind of shape. And if you change the shape and you get a different measure which is scale invariant, and the moment you change the rule and you get another scale invariant parameter, that is where we say it is not just the scale invariant measure, but also the shape dependent measure we require. And that is what is being discussed there. And in remote sensing, as I mentioned, we didn't do much on morphological profiles for classification of hyperspectral images, but very powerful results I could see from the groups of John Benditson, John Sutt, and Lorenzo Bruggione. And grouping of remotely sensed satellite images through ranks for pairs. And we have employed some morphological distances here. And in the geospatial data science, simulation of landscapes, hierarchical morphological interpolations, and skeletonization by influence zones, and weighted skeletonization by influence zones to convert the point specific data into contiguous zonal map, and which can also be employed in generation of variable specific cartograms. And then some spatial reasoning and spatial interaction studies on the spatial data, and how these studies could be integrated to better understand the process dynamics. So that was an open question, and where we have to bring in a lot of nonlinear physics concepts, and that is the way ahead for the people, probably for young generation, to take those studies to the next level. So if this is the data, and retrieval is mostly 90% of our works are relying on, the retrieval. An algorithm will be developed to retrieve certain features and map certain features. But not much importance was given for the analysis of the information that we retrieve from the data, and then its quantitative reasoning, modeling, and visualization. And these are all the topics that we have to really emphasize more in the coming during the years to come. And the mathematical morphology, as I shown, these people, these are the founders. And then very broadly, if someone has interest in mathematical aspects of this particular field, and broadly they have, binary mathematical morphology deals with mostly mapped information, black and white thematic maps. And the grayscale morphology, it talks about the functions like any grayscale images or digital elevation models, to give an example. And all the operations that have come from binary mathematical morphology and grayscale morphology can actually be extended in the graph notations. And for the basic operations and the way using the graph morphology, notations have slightly changed, but it has several other advantages, particularly when we deal with the time complexity graph. On graph domain, the time complexity can be reduced significantly. And adaptive mathematical morphology, it's a very interesting topic, and how to choose the rule to investigate a shape or a function. A function is like a terrestrial surface. And so what is that rule and how to define that rule, and all that would come in the adaptive mathematical morphology. A large number of transformations, and to tell in just 2 words, and morphological erosion and morphological gyrations are the basic operations. And in entire mathematical morphology, there is the data, and there is a data, and then there is a rule to investigate that particular data. There is a rule to investigate that particular data. Hello. Hello. I'll talk to you later. Lecture is going on. Okay. So these operate. There is a data, and then there is a rule to investigate that particular data. And that rule is actually called structuring element. And the data is our own spatial data. How that structuring element will be defined, and there are a family of structuring elements. And if you have a proper justification, and you can actually design and define your own structuring element. That is the key of entire mathematical morphology. The definition and derivation of the topic, like that structuring element, is very crucial and very important. And then based on erosion and dilations, we have the cascade operations. Erosion followed by dilation is opening, and dilation followed by erosion is called closing. And all these are various different transformations which we have used at different places. I don't really go into the details of these equations. So this is actually about X erosion by B. X is an object. B is the structuring element, a probing rule, and with which you will actually contract the object, and it has a dual operation, that is dilation, and dilation expands the object, and the degree of contractions and expansions are depending on the characteristic information of this B. B has certain primitive shape and size, and it has orientation, and it has symmetric properties. And so that B, with that B, and you can generate a host of erosion contracted versions and expanded versions. And then if you keep on applying erosion followed by erosion followed by erosion, and you have nth size erosion, cycles of erosion, and dilation followed by dilation, you have nth time nth cycle dilations. And so these are all on the simple spatial objects in the sense just black and white objects. And then the cascade operation, erosion followed by dilation, if you perform, and you have a kind of a smoothening from inside, and dilation followed by erosion, you have a smoothening from outside, and inner smoothening and outer smoothening, and how they actually, what are their applications on in geosciences and remote sensing. Number of applications are there, and these are the principles they used in morphological profiles to map the information from hyperspectral data. And these are actually called morphological opening and morphological closing, and they're multi-scale versions. And you can perform, if you keep on performing openings with increasing size of structuring element, the sizes of structuring element will be defined with n is equivalent to 0 to some capital N, and it makes the surface flattened. And so the dilation will make the surface gaining energy, and a opening actually makes the system to lose the energy with the increasing cycles, whereas closing would give the system to gain the energy. How this energy gaining and energy dissipation would impact our terrestrial surfaces, and what is that measure that we can really derive and that can be really linked with the process, is a important topic of particularly on when we study the digital elevation models. To have an illustrative understanding, this is an original object with an erosion and it got shrink, and with dilation it got expanded here, and then by performing openings, and this is opening and this is closing, and then you have dilated version, and that is what is written: effect of erosion, dilation, opening and closing using 3 by 3 structuring element. And those structuring elements I would show after a little while. And whatever we have seen on the binary domain, that is just ones and zeros, and if you have a kind of function and like a grayscale image, and where the values are not just zeros and ones, there the values are ranging between 0 to 255. If you are talking about the data is normalized in between 0 to 255 when it is stored in 8 bits per pixel. And you have again grayscale erosion, grayscale dilation, and their multi-scale versions, and then the cascade operations, grayscale closing and grayscale opening, and then multi-scale grayscale openings. You keep on performing erosion followed by erosion followed by erosion for n number of times, followed by dilation for n number of times, with the same rule that is called B, structuring element. You get a kind of grayscale morphological opening closing operation. And this is actually, I have given it in wrong way, and this is morphological opening and this is morphological closing. Actually these symbols were wrongly specified here. And when the rule is not just a flat structuring element like with zeros and ones, and you can choose a non-flat structuring elements, and which is another structuring function with which we have several other advantages. So how they can be employed in this is a typical grayscale information, and which I have shown it in a numerical array. The values are ranging between 0 to 255, and so how we perform dilations and erosions with flat structuring element and non-flat structuring element, some examples are shown here. And this is by using the graph notation. An image can be shown in a graph form, and then on the graph you can perform morphological erosions and dilations, opening and closing, and then you go back to your original image, you make those changes, and you will see what kind of advantage that you get by extending the classical morphological operations to graph morphological operations, right? This is all about some basics of mathematical morphology. And in the Ridge Valley network extraction, look at this. This is a kind of data. This is a kind of a function, I would say, spatial function. If I convert that into a simple thresholded form by using a threshold value of greater than or equal to 0 is ones, and below 0 or equivalent to 0 is background, and you can convert that into simple a kind of theme. And by performing a transformation called skeletonization, you can actually extract this particular skeleton. I would say this is body, and the body contains the skeleton. And if you subtract that skeleton from the body, whatever you see is called, in physical terms, it is called fat fractal. So characterizing that fat fractal is also very important, which would give us scale invariant measures, but they are shape dependent. So how we have employed that, and I would spend more time on that particular skeletonization. And if I'm not sure whether it is visible. There are actually green lines and blue lines here. and green lines are channel networks and blue lines are ridge connectivity networks. And then the possible partitions of watersheds from that particular landscape is it's all about, you know, the idea of transformation called skeletonization is just used here. Then we could get very rich both topological and geometric information here. And there are ways, and so network can be extracted by using simple binary morphology. For that, the data has to be actually decomposed into threshold regions, and then you apply simple binary skeletonization process, and you can straight away apply the grayscale skeletonization process, and each one has its own advantage. But whatever the channel and ridge connectivity networks that you get out of applying the binary skeletonization are more stable. When you apply directly the grayscale morphological skeletonization on the grayscale data, and you get very quickly, but it has certain discontinuities in the network that we actually compute. And this is not computationally expensive, and this is computationally expensive because you have to decompose the data into thresholded regions. Only then you can apply the binary morphological operations. So subsequently, to show one example, and we have a large number of water bodies which were actually traced from remotely sensed satellite data, and we want to find out what is the influence of each of the water body. We applied a kind of operation called watershed transformation, very popular in mathematical morphology, and the watersheds are very popular in segmenting the images, and it has certain difficulties like it's over segments the image if you are talking about a rather complex grayscale image. But if you have very simple thematic information like this, simple water bodies and no water body regions, and the computation of their watersheds or zones of influence is just straightforward, and you will get noise-free zones of influence data. And subsequently, we use their corresponding basic measures of these water bodies and corresponding zones of influence to derive certain power laws. Interestingly, and the power laws that we derived for water bodies and their corresponding zones of influence are following the universality constants but of different classes. The idea involved there is a skeletonization by influence zone technique, and which is precisely what I mentioned about watershed transformation. That is about one aspect of, you know, applying the skeletonization. The other one is superficial roughness characterization and the granulometries, scale invariant but shape dependent power laws. And most of you know, in geosciences or geomorphology, quantitative geomorphology, we take channel networks and then we apply the simple conventional morphometric analysis on the rivers, and then we come out with certain topological quantities called bifurcation ratio, stream length ratio, and then stream area ratios. And then we, from that, we'll infer many geological processes. And typically bifurcation ratio, higher the bifurcation ratio, there will be the tectonic activity will not really disturb the terrestrial surfaces. These are the implications given some 5 decades ago by, you know, the several quantitative geomorphologists. So look at these 3 simulated channel networks, but they all yield the same topological quantities, but it has a different structure. That is where we thought that, and if we remove the skeleton from the corresponding body, whatever we see is the fat fractal body. And typically on the terrestrial surface, they are considered as hill slopes. And is there a way to quantify those hill slope geometry? And for that, we have given an idea and how to pack that hill slope regions with some regular gons. Like you can see this as a kind of Apollonian space. And you can largest inscribable octagon, you take it out, and then on the remainder, whatever the octagons that you can inscribe, largest inscribable octagons, and you take them out. And that is a recursive process. And then eventually we have packed the Apollonian space with octagons of various different sizes. And then here you can derive power laws, and those power laws are not just the scale invariant, but shape dependent. The moment you change octagon to square, octagon to circle, and you see a power law that is scale invariant, but depending on the shape that we use to pack this Apollonian space, and we see a different kind of power laws which are scale invariant. So for that, and we have taken a region and a spatial data. We have computed its corresponding skeletal network, and that skeletal network is when we extracted that, we see when we subtract that skeletal network from that corresponding the outline of the basin, you see this hill slope region in white space, and that has to be packed with non-overlapping disks of various different shapes and sizes. And typically it shows like, and by packing with that hill slope region, which is shown in fat fractal form in a white space, we pack that with an octagons of various different sizes, and then we derive power laws. And those power laws, as I mentioned, and scale invariant, but the moment you change from octagon to square, it gives a different scale invariant measure. And typical geomorphologist can really take the advantage of the shape dependency to link with the actual process involved in that particular terrestrial surface. So some of the results we have shown here, and so what is the advantage? And whatever that you derive through classical morphometric analysis of rivers, or just scale invariant, but shape dependency we cannot bring it, and that's where we have employed mathematical morphology there. Subsequently, we have multi-scale openings on the grayscale images. What will happen? You have a grayscale image, and if you keep on applying the higher cycles of opening on that, cycle 1, cycle 2, cycle 3, up to capital N number of cycles, and it loses its information. A brightened image would become darkened and darkened and darkened. But the way it applies, and so all morphological operations are nonlinear in nature. That is where we have several advantages over wavelet transformations. When we talk about some kind of quantification of the surface roughness, and because of the nonlinear properties of these operators, and we have several advantages. And these are the equations, and I would come back to these equations in the second talk. And you can see illustratively, this is the same digital elevation model of a specific basin. And that basin, when we applied multi-scale openings of cycle 1, cycle 40, cycle 80, a few snapshots we have shown, and they are actually going towards darkened and darkened. At one stage, it becomes completely a kind of black patch. It is, how do you quantify the energy within this basin? And I'll simply sum all the grayscale values here, and how those grayscale value area or the volume is getting diminished with increasing cycles of opening. And whereas in the closing operation, where dilation followed by erosion is involved, and you are actually gaining the total volume area. And because here it disconnects the valleys, here the valleys are getting filled up with the surrounding grayscale values or the elevation regions. We can actually link this opening and closings with typical erosion happening, and then so the eroded material getting dumped on at the valley regions, and it reaches to a kind of convexity, and it convex hull, and it reaches to convex skull, and there is a variation. And look at this, and we have used the probing rule rhombus here. This is the structuring element. If you change that rhombus to octagon, and you have a different way of losing energy. And if you change it to square, you have a different way of losing energy. And from those losing energy, and from cycle to cycle, subsequent cycles, and by following some of these equations, you can actually quantify that roughness value, which we call it as a morphological entropy. And that morphological entropy is nothing but the superficial roughness. And that roughness value would change by changing the rule that you have chosen. Whether it is rhombus, you get a different roughness value. If it is an octagon, you get a different roughness value. And what is that rule that would show you highly rugged terrain with no roughness index? So that is where the adaptive mathematical morphology has to be brought into picture. So those are some of the pictures that you have seen. And then mathematical morphology in remote sensing. And we have seen those two cases on geosciences. And then in remote sensing, very quickly, we have a 1-band data, panchromatic data, and 2 to 10 bands, multispectral bands. And as we are seeing, it is not the spatial resolution and temporal resolution. Now we have seen a large, high spectral resolution. Handling such kind of data, evidently we require more robust algorithms, and those algorithms were actually given by through morphological profiles and extended morphological profiles and attribute profiles, which were very popular in if you are in if you see our TGRS or JSTARS papers, there is a hundreds of papers on these morphological profiles for hyperspectral image analysis. And finally, to map the specific target objects. So not only there, and then you can also apply mathematical morphology, mostly morphological distances, to reduce the dimensionality of these hyperspectral images, and computing the distance between every image to every image. And then you can actually figure out which are those two channel images close to each other. And those out of those two images which are close to each other, you can remove one of those images to reduce the dimensionality. That is, of course, it is an open question, and some of our group members are working on that lines. And ranks for pairs of images, when you have, let us say, 100 images in a database, and then if you are asked to group those images, which are those images close to each other, which are those images which are far from each other, and for that you evidently require, whenever you take a pair of images, so are they close to each other? And what is that we are computing? We are computing areas of infima and suprema of those two images, and then the distances, erosion distance and dilation distances. And this is a simple ratio. And the product of these two ratios would tell you how closely the two images in the pair are spaced. And then can we say that if the rank for the pair is 1, and we say that that is the best pair, as it is getting the value is getting going towards 0, and we say that is the worst pairs. And for that we have given a set of equations, and I'll come back to these equations in the second talk by spending more time. And then so the same ideas we have applied on ranking the pairs, and then we have taken spatial data, we made it into 4 quadrants, and between the quadrant to quadrant, and quadrant 1 to 2, 1 to 3, 1 to 4, and then how those ranks are going. And we have actually given some kind of matrices here. And anyway, I'll share this all these slides I have already shared with Dr. Erturk, and then I think he would place at the proper place for the audience to really download and look at in detail these values. And hierarchically, if you, here we have done only 4 quadrants, and then each quadrant is made into sub-quadrants, 4 sub-quadrants. And if you do this, and then if you compute those ranks for the pairs of the corresponding matrices, and you can figure out which are those two regions are close to each other. And so can we really link that with the process? And if this region and if this region is close to each other, and can we talk about what is the runoff conditions, groundwater conditions, and then other physical, geophysical process? That is a way ahead to really handle. Right, that is about mathematical morphology in geosciences. In geospatial data sciences, there are many cases, and I would see when the time. So I think I can go for another 10 minutes, right, Dr. Artuk? Yeah, sure. And then I would quickly show some slides. And this is about simulation of fractal landscapes and superficial roughness characterization quantification. We have already seen, and then scale invariant. But so this is the simulation and interpolations and spatial reasoning has to be seen. And that is, these are the 4 topics we will see quickly. And synthetic landscapes, what we have done, if you know the boundary of a specific basin, and I have shown in a synthetic form as a fractal outline, and what is the one-dimensional or 1 pixel wide caricature that summarizes the overall shape and size of this particular fractal basin and its corresponding skeleton. I have shown that particular skeleton here, and that skeleton is also order designated according to Stoller-Houghton order designation. And then from there you can actually compute certain the morphometric parameters, but that is not our interest. And here the skeletal subsets ranging between 0 to some capital N. So 0th level skeletal subsets, and 1st level skeletal subsets, 2nd level skeletal subsets, 10th level skeletal subsets, up to some capital Nth level skeletal subsets. If you take the union of all those skeletal subsets, you get its corresponding network. And those skeletal subsets are dilated with the corresponding order, and you will generate the influence zone of that particular skeletal order subsets. And those influence zones, if you take the union, and you can actually reconstruct a kind of landscape within this simple outline of the fractal basin. And that landscape we have given a kind of, the color coding. And so from there we have actually generated these fractal landscapes. This has more interest. People have interest in, the computational geometry, and then fractal landscape generation, mostly to create some kind of scenes close to the realistic landscapes. And I would skip that. And then morphological interpolations, different scenarios. Look at here, and there was a bubonic plague in Indian subcontinent in 1896, and that was spread until 1906 for about 11 years. Snapshots at annual intervals we have gathered, and then between 1896 to 1897, we started interpolating in between by using morphological interpolations. And then between there are several interpolations. So between object A and object B, I can create one interpolation. And between interpolation and object A, I can create another interpolation. Between the interpolation and the object B, I can create another interpolation. This is a hierarchical manner. In 2 power n form, I can generate so many sequence of interpolated images between the object A and object B, such that until there is no further scope to insert one more interpolation. That is the descriptive description that I can provide. And that is the idea we have followed for 1897 to 1898. And that is a hierarchical process. We have created a large number of interpolated sequences. And then that simulation, and but it may not work here because this is a PDF file. I'll try to see if there is time, and I'll try to show those animations further. Right, and that is one interpolation, and we have created between 1896 to 1906 how this epidemic was spread at in a real-time fashion, and we have simulated that one by using binary morphological operations. And this is skeletonization by influence zone and weighted skeletonization by influence zones. And we have, let us say there are 4 states here, and their corresponding skeletons here. A minimal skeletal point is their centroids. And then if I propagate these centroids as if the water body 1, water body 2, and water body 3, and water body 4, and if they are allowed to propagate with different speeds, like as if they are getting flooded, and you can see a kind of scenario like this. And this particular water body is propagating slowly, and followed by this particular water body, and followed by this particular water body, and followed by this. And you can see the floodwater front lines, how they are going and propagating. And this is actually to convert the point specific data into polygonal form. And you can see with different propagation speeds for different seed water bodies, and you can see a kind of a scenario here. And I would say this is one of the interesting topics in computational geometry and digital cartography to generate cartograms. And here we have used, there are 34 rain gauge stations here, and we have their corresponding rainfall, annual rainfall values, and they have to be shown in a contiguous form. And we followed that skeletonization by weighted skeletonization by influence zones, and we have converted that point specific data into polygonal form. And we have certain snapshots with different propagation speeds, how population cartograms can be created. And the similar idea we have employed for the population cartogram of the United States. And so this is where, and I'd see end of this talk, and whether I can show those animations. And then algorithm to compute the morphological medians between, what is the morphological median? You can see it. These are the spatial data of one terrestrial landscape, and this is another region. We just want to show it as a kind of morphing. So a kind of an object A is becoming object B. Perhaps object A is a circle and object B is a square. And how is a square, a circle can be slowly transformed into square, because we require it as if it is transforming in a real-time mode, like a motorbike getting a tiger. And then we can use this morphological interpolations, because they are nonlinear in nature, more powerful than linear interpolations. This is F1 and this is F2, Fi and Fj, and between these two, I have actually created a kind of morphological interpolated median function, and between this and this, I have created one more. Between this and this, we can create one more. This is in a hierarchical way, and we can create, and then by putting them in a sequence, and you can run it like a slowly a function Fi is getting transformed into function Fj. So it's corresponding link I'll see and in the end of the talk. And in the spatial reasoning, and I would very quickly go because of the time constraint, and it is about the core objective is these are the blue things are water bodies, and those water bodies are extracted from this Landsat image. And then here the typical question was governments have money to only protect one water body under severe drought conditions. Which is that water body that has to be protected, because government is facing a lot of financial crisis. And then if such a situation arises, what kind of spatial policy one can give? And how we handle, we have computed every water body to every other water body, the morphological distances. Those distances are not just like Euclidean distance between the points, and the objects to object distances. How do we compute? And we keep on dilating one object until another object becomes part of that dilated version. And that process, we do that for all 66 water bodies here. And then, and we have created a kind of matrix. And from that matrix, we compute column-wise maxima values. And then for all 66 column-wise maxima values, between source to target, source to target, source to target, and then minimum of all those maxima distances of the corresponding 66 water bodies and their destination water bodies would actually give the strategic location of the water body position. And that is the water body we have to protect. We say that this particular topic comes under spatial optimization, and that is what we have actually computed here. And so I can refer to several papers which we published to understand. This is a very simple idea. What is involved here is simple morphological distances, right? And it has several applications, and not only in remote sensing studies, and in image processing, clustering, and finding the what is that centrally located cluster. From there, you want to do the merging process to make the clustered image much simpler. And then this also I would like to, this is about automatic detection of the orientation of any given object. And those objects what we have taken are actually river basin objects at the basin boundaries, and then it's like a patch. And to find out what is its corresponding orientation, is it going towards north to south or northwest to southeast, and those things it can detect automatically. And that is another animation. And as I mentioned, it has spatial economics and spatial demographic studies. Mostly they use the gravity models to compute the interaction between the objects, like from the Newton's celestial mechanics. The gravity model was used in social gravity, social sciences, and we have used for the trade analysis how that gravity model can be modified, because gravity model is a symmetric model. The interaction between I and J is also equivalent to J and I. But in reality, in social sciences, and the country A benefits more than the country B when they are trying to do kind of some interaction due to some kind of trade understandings. So how to show that kind of thing? And it has distance between A to B is different from B to A. And we have asymmetric distances coming from morphological distances. And then location significance. The way we have shown that water bodies and finding out the strategic location, every object in a country or every object in a continent as a countries, and we can find out what is the location significance. We could see exterior states in a country are disadvantaged, and the interior states in the country as a spatial system has more advantages, because people try to flow towards the centrally located region. And that is where we use the location significance index. In turn, the interaction between I to J and J to I are different. So we have set of equations we have given, and we have shown that which are those two states are highly interacting in terms of trade, and these are the states, and then followed by these two, these are the best pairs, and and these are the worst pairs, and there is no interaction between these, the exterior states, and there are actually blue and red things we have put here, and very smaller states and their exterior states. And that is where we have an animation here to show how interacting the things. And I believe I am on time, and probably I took a few more minutes. But to show this slogan again, mathematical morphology is an area of geoscience that most people don't realize will literally change the way they look at Earth. And mathematical morphology, a robust mathematical theory that needs more attention by geoscience and remote sensing communities. And you can see many books and special issues we have edited or written, and where we have actually used mathematical morphology all through for geosciences, remote sensing, and geospatial data sciences. And if, because I have quickly gone through, and if I have to introduce this as a subject, so this actually this entire subject I used to teach for University of Trento for the doctoral students, it would take about 26 lectures, and those lectures, in detailed lectures, were actually given at as a YouTube links here. And if someone wants to take it seriously, take it to heart, and then apply in his or own discipline of interest, I think I would really encourage them to go through these lectures. And I think these lectures would go about 20 hours. And that is all about my first topic. And then the call for papers, there is one, it is open for the public to submit papers. It is on mathematical morphology in geoscience and remote sensing, IEEE J stars. And then to just quickly recap, and so we have done all this, and retrieval of information, quantitative analysis, reasoning, modeling, and is there a way that we can really construct system specific attractor? If I'm talking about sand dune, and is there an attractor with which we can predict and how that dune will behave? We have spatial resolution data, and across spatiotemporal resolutions and spectral resolutions. With all that data, we have powerful methods to extract the information. And then can't we really go for some kind of nonlinear physics ideas of constructing the attractors to find out whether it is strangely behaving or simply behaving? And so that is where I mentioned how these studies would be useful. And I don't take much time, and the attractor actually looks like this. It's a logistic attractor, and it tells about the behavior of a specific system, and which was actually given by for insect population by one Australian mathematician. And can't we really give that kind of attractors when we are studying a large number of both physical and anthropogenic systems, and why we should not really think about that? So for some kind of lakes and how they behave and their corresponding attractors, and then for sand dunes, these are all simulated. And so the too many questions. So when we talk about big data, but the open challenge is, can we construct system specific attractors with all these ingredients? Addressing such a challenge may provide rich clues and insights in our studies and struggle to make precise predictions. At the end, this is not a job of one person. A great teamwork with excellent coordination is required. And so before leaving it to question and answer session, I should acknowledge that IEEE Geoscience and Remote Sensing Society for giving me an opportunity to be as the distinguished lecturer for this coming 2 years. And then most importantly, Turkey GRSS chapter. This is my first ever opportunity as DL to give a talk. Thank you, Dr. Uzgun, and then I hope he will recover very soon. I want to talk to him. And then Dr. Turk, and then Taskin, Madam Taskin. Thank you very much. And so it's open for the questions.
Thank you, Dr. Sagar, for this overview of a relatively large topic, as you mentioned. It was a good talk. If the participants have any questions, they may feel free to ask now. We have some time. There is a single question in the chat. It's regarding watershed segmentation. The questioner asks whether you think or believe that watershed is outdated.
Yes, that is what is given here. Is the watershed segmentation morphology an outdated method? The concept looks similar, but rarely mentioned nowadays. Yes, it's a good question, but I would say uh, the watershed transformation and probably the classical watershed transformation, which has several difficulties because it leads to over segmentation when we talk about when we are handling a grayscale image. And that is actually not because of the watershed transformation itself. It is because of the lot of noise that images contain. But how to filter that noise? And many a times I used to get this question, how accurate are your algorithms on DEM? And I said that DEM comes with a lot of uncertainties and errors. And the moment DEM is completely noise free, all these algorithms, which follow a kind of genesis, a kind of genetic process, and it actually follows watershed process. If there are two laws, regional minima, and if there are these are water bodies, and if they start growing, and then obviously the line where they extinguish each other is the watershed line. That is the principle. But for the person who has asked the question, and I would really refer him or her to look at the power watersheds and watershed transformations uh, on graph morphology. And I can say that very powerful graph-based watersheds were applied of late, and they are still in, theoretical research, but they were published in IEEE TPAMI. I can say power watersheds concepts, and those power watershed concepts was not even so far brought into the remote sensing data analysis. But I still say that if when you talk about the kind of mechanism is different when we acquire the image like SAR data, microwave sense data, and it comes with a lot of salt and pepper noise and speckle noise, and that applying watershed transformation there is a completely disaster because we don't know. So because it generates very spurious over segmented zones, and systematically merging those zones to make it more meaningful is a real big challenge. I agree with the person who has questioned this, like yes, watershed is very sensitive to noise, but if I have the noise free data, watershed is such a wonderful transformation, and it has different names and flood simulation technique, they say immersion simulation, watersheds, and then the water drop concept. And I can actually explain on the board, but not at this platform, and how watershed functions. And you have a kind of 1D landscape, and you put some holes at the valleys, and then you allow water to ooze through, and then where exactly it meets. And if you have wrinkles within this landscape, 1D landscape, and obviously it creates sub watersheds there. But systematically merging those over segmented zones or the sub watersheds in my language is a real big challenge, but that has been very nicely addressed by through power watershed concepts. And if someone can really refer Professor Laurent Nazman's group works, and University Paris East, and he is my great collaborator, and we both have produced a PhD thesis on power watersheds applying through graph morphological notations.
Thank
Yes,
you.
there is other.
We have another question. This regarding the link between level set approaches and mathematical morphology, whether there is a link or not.
Yes, and I could see that level sets are the terms proposed by Professor James Sethian from UC Berkeley. I would say that they are like thresholded sets. Thresholded sets. And so if I'm working on successively thresholded data, and it is as if working on level sets. Yes, there is a link. And so if I'm working by applying binary mathematical morphology, I prefer to use, first I'll decompose the given function into thresholded sets. and simply in a black and white sets, and then they are nothing but the level sets what the gentleman is referring. Yes, it can be. Yes, there are some studies. Yes.
Okay, any other questions from the participants? Okay, I think due to the time constraints, we may move on to the second lecture on this topic. It's also pretty much related and a continuation of these subjects, so I think we can go on. What do you think, Dr. Sagar? Is it okay for you?
So shall I just take just 2 minutes break?
Sure. Sure,
Yeah,
we can.
just 2 minutes, and then I'll start the second topic.
All right. We are giving a short break, everybody, and then we'll go on with the second lecture. In the meantime, if you have any more questions that you would like to ask, feel free to ask via the chat, and we can ask them later, probably by the end of the second lecture.
Yeah, so I'm ready with the second talk. Yes, and Dr. I'll start. And this is the second part of the talk, and which is again a standalone topic. And those who have not followed the previous talk can easily follow this. But here, the processing and analysis of digital elevation models via binary and grayscale granulometries, morphological interpolations, and morphological distances. And so we have seen a few snapshots of those results, and where I have specifically applied granulometries and interpolations, skeletonization, and morphological distances. And you would see their corresponding equations. And if someone has any doubt, and I can stop and I can actually explain on the board, and which would be much easier to understand. And this part, and so just to motivate, the spatial data is the digital elevation model. I would say it is an engineering marvel, and I know that billions of dollars were spent on generating the digital elevation models. So I would still say that it is not being heavily used, and anyway, this is an important source of data for geoscientists. And of late, I have written a opinion piece for IEEE GRSM, I think, which would be published in this the fourth issue of this year. And so what does it have? And DEMs are with rich but hidden geometric, morphologic, and topologic. I would say this is GMT quantities and the associated parameters. And meticulously retrieving that geometric, morphologic, and topologic hidden quantities from digital elevation models would offer us many insights, particularly for those who are studying the terrestrial surfaces. Or I have seen lunar surfaces. There is a lot of interest, and they are getting very high resolution digital elevation models. And then the relevant mathematics, I realized having expertise in mathematical morphology and fractal geometry, and for that matter, any other mathematical field which has a lot of geometric rigor, would be a huge advantage to unravel these unique quantities which are hidden in DEMs. And of course, certain associated parameters can be derived from those quantities. And we also could see there is a lot of science that we can get out of such kind of spatial data, that is studying DEMs and geometric, morphologic, and topological quantities and associated parameters across space-time and scales, and facilitate researchers derive important science outcomes to develop models through which one can better understand the dynamical behaviors of several terrestrial phenomena and process of the Earth planet and Earth-like extraterrestrial planets. And we have the DEMs coming from Martian surface, Venus surface, and lunar surface, and we have our own terrestrial surface. So to give what are these geometric, morphologic, topologic quantities, and just to mention a few, the peaks, peaks, and global and local minima and maxima, the contours, and most importantly, granulations in contours, and unique valley and ridge connectivity networks, and topographic depressions, and the flat regions, mountain objects, and many more. And their corresponding associated parameters include what is the width function of the watershed that we partitioned on the digital elevation model, and how do we compute the width function. And we have seen conventional width function, which is coming from the classical mathematics, but is there any other way? And we could see that the geodesic spectrum based width function would tell between the thresholded elevation regions and how it behaves and how that width function looks like. And will it really give some insights to the geomorphologists to interpret the process within the watershed, is a kind of interesting topic. And then roughness estimation, we have already seen the simple granulometric analysis based images, but how we actually employ them with respect to the morphological equations. And it is not just the global roughness parameter. And by changing the rule, what I was telling in the previous talk, structuring element and how that structuring element looks like, and how, so with different directions and how it gives a different roughness measures, and how they can be related to the natural process. And structural and textural complexity, basin geodesics, basin stage classification, to relate whether the basin that we are studying, the terrestrial surface, is in the old stage or monadnock stage or the younger stage. And they have some, classical methods like hypsometric integral studies. But all that can be actually replaced with the mathematical morphology based studies with the advent of digital elevation models, and that classical morphometric and hypsometric tools have nowadays no much place for that. And feature mapping and quantitative characterization, reasoning, modeling, simulation, visualization, we are seeing. And again, this is the slogan I put, and digital elevation model is an important source data for those who study Earth's surface. Processing analysis of DEMs, 5 cases that I have shown, how skeletonization was used, and we have already seen the extraction of the river networks. And then the granulometries to compute the roughness, geodesic spectrum to compute the width function like spectrum, which is more refined than the classical width function, and morphological interpolation and morphological distances. These are the topics that I have taken from mathematical morphology, but how they were applied on DEMs is the topic. And you can also see from the previous talk, these are all I have put here only synthetic DEMs, and the TOPSAR DEM, and this is a SRTM DEM, and these are again the TOPSAR DEMs, and some DEMs we have actually downloaded to explain our ranks for pairs of images, and how we have explained that is given here in this particular topic. So mathematical morphology, so DEMs, an important source data for the geoscientist. And so this is the opinion piece that is going to be published probably in the next week in our IEEE Geoscience and Remote Sensing. And what we have argued here is, and DEMs are with a lot of rich information, but if geoscientist is familiar with certain kinds of mathematics like mathematical morphology or fractal geometry or wavelet theories or discrete mathematics or fuzzy set theory, I think the way they look at that particular data is entirely different from how commercial softwares are actually giving the features from digital elevation models. And that is what is written here with some arguments. I think people would take it in a positive sense. And we all know that there are many terrestrial and Earth-like planetary DEMs, and starting from synthetic DEMs, Astrid Global DEM, NASA DEM, and SRTM DEM, Cartosat DEM, Spot Stereo DEM. And but whatever the DEM that we get from analogous data and then through optical images, I think there will be a lot of uncertainties and errors, because if we want to see the ground height, not the height of the canopy on the ground, and that is where microwave the SRTM like DEMs and this Astra DEMs and LIDAR DEMs have huge advantages. And Martian DEMs certainly, and these were not really affected by anthropogenic activity, and we can do a lot of derived science outcomes from studying those DEMs, as long as they are high resolution DEM. I was a part of this Chandrayaan DEM studies, and so Chandrayaan was Chandrayaan 1 mission and Chandrayaan 2 mission. We have in Chandrayaan 2 mission, we have seen very high resolution digital elevation model of lunar surface through optical high resolution camera DEM, and which is 25 centimeters resolution DEM it gives. And we could see the small rocks and pebbles on the lunar surface and through this DEM. And so these are the DEMs, and I would show and how we have applied. This is synthetic DEM and TOPSAR DEM. This is wherever we talk about the topography, and this is the bottom topography of San Francisco Bay, and it has a very interesting flow field structure, and how we have studied that flow field structure, of course, which requires a lot of validation through morphological operations, and I will show some cases on that. And then these roughness calculations for global roughness values for each watershed that we have partitioned from this SRTM DEM, and these are the source data that we have used for the subsequent slides. And some of the, if you are thorough with this mathematical morphology notations, equations, and transformations, and their corresponding illustrative interpretations and descriptions, and it is easy to actually venture into this particular field. So this is not too difficult mathematics. I could see in the audience Salim Aksai is there, and I remember he has published several papers applying this morphology on DEMs. I'm sure many other audience can really venture into this field. And these are some, when we talk about sets and spatial objects, and these are the notations we use. And B is a structuring element. And this is a function, spatial elevation function over X and Y spatial coordinates. Typically like our digital elevation model of a specific region. Area of the function or the volume of the function, it is nothing but the sum of f of xy over all xy positions is actually the area. How that is getting changed when it is perturbed due to the morphological opening and closings, or the cascades of openings and closings, which we call as alternative sequential filters. And then B is a flat structuring element, G is a non-flat structuring element. And where do we exactly use non-flat structuring element? When we are trying to pair the images, what is the rank for the pair of images? We see certain problems when we use flat structuring elements. That is where we have to go for non-flat structuring elements to actually make a kind of relationship between the images in a specific pair. And what is that pair? And I say ith function and jth function. And then dilation, erosion, closing and opening symbols, and then intersections and unions, and infima and suprema, and again intersections and intersection of xi and xj. If it is equivalent to union of xi and xj, we say that these two are identical, which is same case with the functions. The infima and suprema, when they are equivalent to each other, point-wise minima and maxima are exactly the same. We say f and fj are the equivalent things. And then the simple algebraic difference between the areas of the function, ith function and jth function, and this is how we do it. This is point-wise algebraic differences. And then other notations are distances. As I mentioned, object object I and object j, and what is the dilation distance between those two things, and how do we actually compute that, and which would be nice if I can explain on the board, but there's no much time. And erosion distance between object I and object j, and Hausdorff dilation distance and Hausdorff erosion distances, which we have actually used in morphological interpolations. All these distances, where exactly we used, and ranking for pairs of images, and then morphological interpolations, and then strategic set identification, and then of late we are using them in the band selection from the hyperspectral image cube. And then how do we compute the area under the function when fi and fj are taken as an infima of fi and fj, and their corresponding suprema of fi and fj and corresponding areas. And this is nothing but, point-wise minimum between fi and fj you will take, and then you take the sum of all those values, whatever the output that comes. And some point-wise maxima you take between fi and fj, and then the sum of all those values that comes in the output. And that is how we compute. And then dilation distances between ith function and jth function, erosion distance and ith function and jth function. And if you are familiar with, I think they are there in the subsequent slides. And then binary erosion, binary dilation, binary opening, and binary closings, and their multi-scale versions. And when you are performing erosions recursively, erosion after erosion after erosion, and until it gets vanished, and there is a concept of size there, and we can compute, we can tell about the size of the object X without actually computing the number of pixels with respect to B, and we can actually give a kind of equation to study the concept of size of the object X. And similarly, we have, if you keep on dilating an object, it occupies your whole monitor space, or if it occupies the whole universe. and openings and closings, very powerful nonlinear morphological operations. As I mentioned, opening smoothens from inside and then closing smoothens from outside. And these operations actually provided the basis for very popular morphological profiles and their applications in the hyperspectral image classifications and their grayscale versions. So grayscale erosion, dilation, opening and closings, and then their multiscale versions actually opening and closing both in binary and grayscale. They are idempotent operations, and if you perform once and if you repeat the same thing repeatedly, you don't see any change from the second iteration onwards. But if you perform them in a multi-scale form and you keep losing information from the function with increasing cycles of opening and with increasing cycles of closing, and your function gains the information until it reaches its hull, and beyond the hull, and it reaches to morphological convergence, and you don't see any changes. So how the rate of loss in the function under the cycles of opening would prompt you to compute a kind of probability initially for the pattern spectrum and then subsequently for the probability, and using that probabilities p log p, the Shannon's entropy equation, if you apply, and you can compute the morphological entropy or the uncertainty index of that particular function, which is again B specific. The moment you change B, and your pattern spectrum will change, and your probability value will change, and eventually morphological entropy will change. The morphological entropy for foreground is a granulometric analysis. Computation of morphological entropy for the background of the function comes under anti-granulometric studies. Granulometries and anti-granulometries are very powerful tools in both in geoscience and remote sensing, and they are actually size distribution filters and shape based distribution also you can do it, and by tuning the characteristic information of B. And as I mentioned, it's a B dilation by B dilation by B and so on up to n number of times is nothing but the nth size B, and B has characteristic information, its shape, and primitive size, and then as you keep on increasing its sizes by dilating B with B and B with B, and then you can actually increase the size of B. And probably I'll show in subsequent slides just to glean what exactly is B and how they look, and so how it shows impact on the functions and the sets. And so these are the equations, like we translate elements of X with respect to B. And so by following this simple set property, and intersection of all those translates would actually give you a contracted version of X. And its dual operation is dilation. Its corresponding property is you have to translate each element of X with respect to B in such that, and the intersection of that translate with respect to X should always be not equivalent to an empty set. And taking the union of all those translates of B following that property would get you expanded set. And then opening, as I mentioned, and erosion followed by dilation, and it removes the sharp peaks, and it smoothens from the inside, and sharp peaks would be lost, and a corrugated structure would have a rather smooth outline. And then this is the closing and dilation followed by erosion, and this you have in a cyclic form, and their corresponding multi-scale opening and closings. And if you perform multi-scale opening followed by multi-scale closing, you have alternative sequential filter black, and this has many applications actually in morphological profiles and extended morphological profiles, and they have used only simple openings and closings, and if you use them alternatively in a cascade form, you get even finer details. So I think I have not seen that particular paper where they have used alternative sequential filters and to generate the morphological profiles. And its corresponding dual operation is first start with closing followed by opening to the multiple scales, and you have alternative sequential filter white. Actually black dominates here, and then here in the output white dominates here, and in between intermediary grayscales, and they'll actually get adjusted accordingly. So these are the structuring elements I was talking, and it's a flat structuring element with origin at the center, and you have 8 connected circle, they say 8 connected circle, they say it, and then you have 4 connected circle disk, they say it, and then this is a symmetric structuring element, and if you rotate it this around about the origin to 180 degrees, if it's the same, I would say B is equivalent to B transpose. As long as B is equivalent to B transpose, I would say whatever the morphological operation that we perform are actually equivalent to Minkowski sum and Minkowski subtraction, and which are actually similar to morphological dilation and morphological erosion, as long as the B is equivalent to B transpose. If you change B to asymmetric type, and the origin, the moment you choose at this corner at the vertices, and if you rotate it to 180 degrees, and then you cannot say B is equivalent to B transpose, and in turn it is an asymmetric structuring element. But whatever that I show in the subsequent slides, all that are the results that we generated with symmetric structuring element. With asymmetry, you can see it. And what happens if you increase the size of this particular 8 connected disk? This is, let me say this is B. If you dilate this with itself, and you get a bigger size B. And if you dilate this with this, and you get still bigger size this. And this is how size increases when you increase the size of B with respect to N. I'm using N ranging between 0 to capital N. And the same structuring element, look at this, and a symmetric structuring element, and you can decompose this into directional structuring elements. So this is, I would say this is B, and this is B1, B2, B3, and B4. And taking the union of B1, B2, B3, B4, you will get back your original structuring element. But performing all these morphological operations that I have shown in the previous slides, and instead of just a compact symmetric structuring element, if I use one-dimensional structuring elements, perform granulometric analysis, which is nothing but multiple scales of cycles of opening operation on the DEM, and you get the loss of information, because it also reduces the energy, because we are performing opening, and that loss of energy with respect to this, with respect to this, with respect to this, and would be completely different. And in turn, we can get the surface roughness with respect to this is one particular roughness index, with respect to this another roughness index, with respect to this another roughness index, with respect to this one you get another roughness index. All that would be different. And if you want to decompose this structuring element into 8 directional structuring elements, you can use them like this. And this is in this form, and B1, B2, B3, B4, and B5, B6, and B7 and B8. And so 8 types of way you can actually decompose that. And these are all flat, because we are only using zeros and ones. If you use a specific distance function, and you can actually generate and use non-flat structuring elements, which I have not shown here. And you have seen these pictures in the earlier slides. And then extending those binary morphological operations to grayscale, and erosion of the function by B is nothing but within where ij belongs to the structuring element, within that window, whatever is the minimum value, you replace the central value with that minimum value, and you have performed a kind of, one step of erosion on the grayscale function. And instead of minimum, if you take the maximum within that window, ij window belongs to B. And again, B can be anything. B can be a 8 connected disk, or 4 connected disk, or some asymmetric structuring element. If there is a justification, you can use asymmetric structuring elements. And performing their cascade operation, erosion followed by dilation, you keep losing information in the function and gaining information. And you have their multi-scale versions. And you have also the alternative sequential filter black and alternative sequential filter white on the grayscale functions. And when you use instead of B, which is a flat structuring element, if you use G, which is called a structuring function, which is non-flat, and you have the same notations and equations here. And their corresponding examples you can look at here. And with flat structuring element on a specific function, and with non-flat structuring element within a specific function, you can actually make inferences from this. And this also you have seen on a graph domain. And so, as the title says, it is all about how skeletonization, granulometries, morphological interpolations, and morphological distances can be used in on a DEM processing and analysis. Then more than the processing and the analysis part, and because we quantify many things, and the skeletonization, skeleton of a set, a black and white object, as someone has asked the level set, and I would say that that set is a kind of thresholded set decomposed from the function by following a simple threshold decomposition equation. And then for that, and so what is the skeleton? A 1 pixel wide caricature that summarizes the overall shape and size of X. And from that skeleton, I can reconstruct exactly the set X back. And if I follow some dual operation. And so this one is actually computed by taking the union of all skeletal subsets of order n ranging between 0 to capital N is the actual skeleton, where the skeletal subset of order n can be computed by eroding the set X by n size B, and that eroded set should be opened with arbitrary size B so that it filters out the granulations of the set X, which are actually flow paths of the streamlines, because I'm relating the skeleton here with our valley connectivity network on the DEM. So this is the equation we have used on the thresholded elevation sets that are decomposed from the grayscale digital elevation model. And then, so that is about the skeletonization. And the distance between xi and xj is nothing but minimum of n, such that when xj, object xj, becomes the subset of the xi dilated by n size b, because xi and xj may not be exactly overlapping on each other, and probably they are partially overlapping or completely disconnected. You keep on dilating set xi until xj is contained in the dilated version. That is how I mentioned minimum n that satisfy this property would get you the dilation distance between xi and xj. And similarly, dilation distance between the converse is xj and xi. And as long as xi and xj are identical in shapes, you don't get this, the other way is equivalent to this particular dilation distance. So this is one condition in when we deal with in a binary morphological distances. And similarly, for erosion distances between xi and xj, and instead of dilation, and you make sure that ith set is eroded until that becomes a part of xj, and then it is also not symmetric distance. E of xi xj is not equivalent to erosion distance of xj and xj, and it has if xi and xj are identical and these two distances are same, and xj and xj are identical, these two distances are same. And we have some other things like morphological interpolations between the sets. And what we do here is intersection of xi and xj, you keep on dilating with n ranging between 0 to capital N, and union of xi and xj keep on eroding with n size b by increasing the size b from n is equivalent to 0 to capital N. Take the intersection of these two outputs, and then take the union of whatever the intersection outputs that you are getting, you get a typical median function between xi and xj. And this can be actually heavily used in the predictive analysis. And you have object A, let us say a tumor at time t, and the same person's tumor at time t, how it is actually deformed and changed its size and shape. And then you have the time gap in between the t and t plus 1 is, let us say, 6 months. And then if you want to find out how this tumor has evolved from xi to xj over a period of 6 months time, and we can actually create interpolations in a hierarchical way, one interpolation and then interpolation and the source tumor and interpolation of the target tumor. You can create another 2 interpolations. You can create interpolations until there is no further scope for you to create hierarchical interpolations, and put them in a sequence, and then you can run it and you can see as if you are seeing the tumor evolution, geometric evolution in a real-time mode. And it's a dual operation. It's a whole mathematical morphology is with full of dual operation. Erosion is dual to dilation, and dilation is dual to erosion. Opening is dual to opening, the closing, and closing is dual to opening. And alternative sequential filter, black and white, are the dual to each other. And the median function is a dual to its dual median function. So, and then this is all about distances and the medians. And then you have uncertainty index calculation. I was talking about computing the pattern spectrum. Pattern spectrum is typically this, and you compute the opening of X and opening of X by with the increasing cycle of B, and you take their corresponding areas and you take the algebraic difference between those 2 outcomes, and you get the pattern spectrum of X with respect to B at the nth level. And you keep increasing n from 0 to 1, 2, 3, and you can actually compute a set of pattern spectrum values, which would actually quantify the shape size spectrum of X with respect to B. The moment you change B, you get a different kind of spectrum. And that those spectra values, you for different n values, you divide with the total area of the set X, and you get probability values. And those probability values at nth level, and from n is equivalent to 0 to capital N, you compute this Shannon's entropy, P probability log probability. And then negative of that is actually uncertainty index, which is nothing but the roughness index or the morphological entropy, you can call it. So extending these things to the grayscale functions is simply, instead of set X, and you are using morphological, set X, you are using the function, and the operations are actually grayscale morphological operations instead of binary morphological operations. And instead of intersections and unions, we are using suprema and infima, and you can compute the grayscale skeleton. And it has certain disadvantages, because if the image or DEM comes with noise, and you will see a lot of discontinuities. And that is where I would always say that decompose the DEM into thresholded elevation, elevated regions, and then apply skeletonization and systematically make them superposed, and then you get the actual skeleton in the function. And there, similarly, the granulometric uncertainty index is, instead of binary operations, and you are seeing the grayscale morphological operations, grayscale opening here and grayscale opening with to the increasing cycle, and subtract that, take the algebraic difference and compute the pattern spectrum value, divide that pattern spectrum value with the area under the function. As I mentioned, sum of all the values in the energy function or the function F or the DEM, and you get the probability values, and then for that you compute. Typically, it gives the texture index for the DEMs or the any surfaces. And similar to morphological, binary morphological interpolations, and we have a grayscale morphological interpolations, you take infima of Fi and Fj, and you take suprema and Fi and Fj. Infima is dilated and suprema is eroded, and take the infima of these 2 outputs and take the suprema of all those outputs that you are getting from this and this. And then you get the median function between Fi and Fj. And so instead of doing infima here, and if you take suprema, if you take instead of doing suprema here, and if you take infima here, and you get the dual morphological median, and then you have dilation and dilation distance and erosion distances. Unlike in binary case, dilation distance between Fi and Fj is also equivalent to dilation distance between Fj and Fi, and which is symmetric. And then this is how we compute. We take the areas of the suprema, and we keep on dilating the suprema of Fi and Fj until its corresponding area becomes larger than this, because you know that infima is always lesser than or equal to suprema of the corresponding functions. And in the same way, instead of dilation, if you use erosion here to satisfy this property, you get erosion distances things, right? Sorry, and this is I think this is got strong. Okay. So as I have shown in the previous slides, and if you want to go one by one those lectures to understand what is simple skeletonization, and I have actually taught them on the board and in a simple slides, and one can, I recommend the audience to really look at it as long as they have interest. And then subsequently their applications, and so with the skeletonization, oh, sorry. And so let me just open the PDF file, and that would be easier. Yes. Sorry for the interruption, and then I'll just take. Yes, and full screen. Yes, skeletonization. How we use the skeletonization? I would skip all these things because you have seen these pictures, and it is like when this is a kind of synthetic function, and by threshold decomposition, I can make them into thresholded elevation sets like this. And for each of the thing, I'll compute the skeleton by following the simple skeletonization equation, and systematically those skeletons will be taken as the union, and then I get a kind of skeleton like this, and I would say this is the valley connectivity network for this kind of function. And that is the idea. And you can also directly apply on the grayscale DEM, and instead of decomposing into thresholded elevation regions, and you can apply these channel and ridge connectivity operations. And if you do that with instead of compact structuring element, one dimensional structuring element, and you can mostly avoid that connectivity problems in the output. So this slide also you have seen, and I think this is an enlarged version, and this is what we have computed from that synthetic DEM. And by applying that simple skeletonization process, and this is green lines are the valley connectivity networks, and blue lines are the ridge connectivity networks. And so this is the unique topological connectivity networks. And then synthetic landscape also I have shown in the previous talk. And the idea that we have used is simple skeletonization, binary skeletonization. That skeleton looks like this, and we have actually order designated with different colors, and then we have generated when we try to reconstruct the original object, and the skeletal subsets would be dilated to the same order, and then we color coded them and then taken as the union, and then we could generate this kind of a colorful fractal landscape. And then when we have shown with different vertical exaggerations, and this is how we have actually explained. And then this granulometries, as I was talking, these networks are topologically invariant, but why they are topologically invariant, and the topological quantities that we compute from all the three networks would yield the same topological quantities, bifurcation, stream length, and stream area ratios. But what is that basic measure that would show the basic distinction between the corresponding basins and their corresponding process, which actually possess this kind of river networks within those basins? And that is where that was the objective for us to go further, and where we used the morphological shape decomposition, and how morphological shape decomposition can be done. And you perform nth capital nth level opening cycle on these, and n plus 1th level it vanishes because erosion dominates and there is nothing more to be dilated, and in turn you will lose everything at the n plus 1th level. At the capital nth level you may see one small dot here, and that one, you to the same capital N levels, you keep dilating it, you get this block, and then subtract that from the original Apollonian space, and you get a halo here. And then on the remainder you do the same process iteratively, and then you color code them and you systematically you union them. You see that it is a kind of packing the Apollonian space with octagons. It is like a sphere packing studies, and but in a discrete way we are doing it. And if you keep changing the octagon to square and circle and triangles and many other shapes, and you keep getting different power law values which are scale invariant but shape dependent. So this is also, you have seen, as I mentioned, the whole DEM, I look at it as a kind of body. In that body there is a skeleton. Typically the river network on the DEM is the skeleton, and if I remove that skeleton from the river net, the whole basin, whatever that I see is a fat fractal or the hill slopes in geomorphological language. And those hill slopes, if I can pack with the same idea of morphological shape decomposition, and I can compute scale invariant measures, but they are shape dependent, which would be highly useful for those who are studying the geodynamics and geomorphology. This is what I was referring. From DEM, we have converted that into a kind of black and white patch, and by using simple thresholding, and then correspond the skeletal. Yes, and how much time I can take?
Well, we started about 10 minutes later, so we may have more time, but keep in mind that we also need some time for potential questions. So,
Yeah, yes.
I'm leaving it to you to arrange the time period left for questions.
Fine. And probably I'll take quickly, I'll wrap up, and then, so is there any question that I can answer in between? That's also fine. But I'll wait
Yes,
until...
not currently, though our participants may feel free to ask now.
Or I'll wait until this is over, and then at once I can answer the questions.
Sure.
Yeah. So, this is how when the skeletal network from the basin that is actually decomposed from the DEM is subtracted, and we see the hill slope regions in a kind of set-like patch, and then that we have to apply. That's where we apply the morphological shape decomposition, and in turn you pack that hill slope region something like this for different basins, different packing we have shown, but the shape that we have used is all through the octagons, and if you change the shape you get a different power law relationships. And these are the equations I have already shown in the tabular form, and this is the pattern spectrum, this is the probability, and this numerator is the pattern spectrum, and denominator is the actual energy under the function. And then once you compute these probability values, and you can compute the uncertainty index. And this also I have already shown in the previous talk. And so how this is losing its energy and how it is gaining its energy. The systematic, it is not systematic. It is the loss of energy is in a nonlinear fashion, because the transformation that we are using is our opening and closings, which are nonlinear operations. And then with different structuring elements, we have seen a different patterns of losing energy. and their corresponding average roughness values for all 14 basins actually we have taken, and then we have computed it here. And so this is where the extension from the previous talk, and all this we have done with a compact rhombus, octagon, and square. But from the square, as we have, if you recollect from the earlier slide on structuring element, and we can decompose that a square-like structuring element, symmetric structuring element, in 4 directions, and north west to southeast, and north east to southwest, and then north south, and some east west. And for with those structuring elements, when we compute the uncertainty index, and we get for different basins with different directions, it is having high directional roughness values. In whichever direction it has a high roughness value, we have actually shown them in a kind of that particular direction hatching here. And this particular watershed has high roughness in this particular direction. And this watershed has in this north-south direction, it has roughness. And so this is the high directional roughness based map, and this is lowest directional roughness values. In whichever direction it has a low roughness value, and so this is how we have done with the same granulometric analysis, right? I think these are some of the pictures that I don't like to go into, but what happens when you are keep on performing opening with increasing cycles? So you can see 10 cycles, 100 cycles, 1000 cycles, and 10,000 cycles. What happens within the basin? And so if you change the directions, B1 to B2, B2 to B3, B3 to B4, and at 100 cycles, how the whole DEM looks like. And with 0 cycles, with the same structuring element of same watershed with different possible structuring elements at different cycles, and different structuring elements, how they actually look, and the way they are looking differently, and actually the energy that it is losing is also losing it in a different way. Right, this is how we have done the directional granulometric analysis. I would actually skip this particular part. This is geodesic spectrum based width function. And so these are some simulated studies. And on San Francisco Bay, so this is a small portion, and it is corresponding enlarged version. And then how the flow fields within those bottom topographic thing. If you follow a simple width function thing, and you don't see so many the flow field structure variations, and their corresponding width functions were computed not through actually classical width function equation, through geodesic spectrum equation. And these are also again grayscale morphological operations. You have seen interpolations. And so this is the source and target. Between the source and target with the different styles, with flat and non-flat structuring elements, how we have created the hierarchical median functions. So this is also you have seen, and these are some videos, but I could not show with the flat and non-flat structuring elements, how we have shown, how one particular function is slowly transforming into other function. I think with non-flat structuring element, we have several advantages. These are for the ranks for the pairs, the equations, and their corresponding properties. And this is what, and when we made it into 4 quadrants, and which are the best, which 2 are the best pair here, which 2 are the worst pairs, and for that we have computed distances and infima suprema ratio, and erosion and dilation distance ratios, and then the product of them, and we could create a kind of matrix here. Obviously, quadrant 2 itself is the best pair, and then with other quadrants, the higher the value, the better is the pair, and that is what we have shown. And then at the overview, and I could cover skeletonization, granulometries, geodesic spectrum, briefly, morphological interpolations, ranks for pairs of images. And then I would always say that digital elevation model is an engineering marvel, an important source of data for geoscientists. This is the slogan I was talking. This is morphology, a robust mathematical theory that needs more attention by geoscience and remote sensing communities. And this is again the call for paper. And thank you so much, and for particularly to GRSS Turkey chapter for hosting this talk through webinar. And I'm really grateful for patiently answering my questions through emails, several emails. And with this, yes, I stop. And So it's open for question and answer session.
Thank you, Dr. Sagar, for this interesting talk. And it seems we have one question. It's what is the roughness value reflects for watershed or any segment of DEM?
The roughness value is a kind of the numerical value. Like if you want to normalize between 0 and 1, you can actually normalize. Or the higher the value, higher the roughness. So as I have shown, that is actually morphological entropy. P log P, summation of the P log P for all orders ranging from n is equivalent to 0 to capital N. And it's actually a texture. And if in simple image context, it's a kind of texture index. And because I am using digital elevation models, and I would prefer to use the roughness, the terrestrial roughness.
Okay. Could you kindly provide us with some quick insights on new opportunities and potentially new challenges on these topics? What do you expect in the near future?
Yeah, you mean on DEM studies or in general image processing or image analysis?
DEM or in morphology? You can
Yes,
answer either one.
yes. And I could see mathematical morphology has a great role to play in spatial data sciences. As I have shown at the end of the last talk, the previous talk. So if you talk about like the sand dunes, and it's I would call the sand dunes are there at those places, but its superficial geometry is getting often changed with wind action and several other actions. And but studying the DEMs of dunes and their corresponding roughness spectrum and with all directions, and I have only shown for 4 different directions, but we can increase the number of directions. And if you do that in a differential way at different time periods, and what is, I'm sure that we can actually extract some scientific outcome from that. That is from the science point of view. But mathematical morphology, yes, in engineering context, it has been heavily used in computer vision studies and in medical image processing, and of course in remote sensing, as I mentioned, morphological profiles and extended morphological profiles and attribute profiles. So they have used them in hyperspectral image classifications. And in band selection, yes, morphological distances have a great role to play, and but not many takers for the simple reason many people think that morphology is a small portion of image processing and image analysis, but I can say it is one 3-credit course, and one can really offer. And that is where actually I have shared those YouTube links in the slides. I think one can have a look at it, and some lectures were like overview lectures, talks like this, and then some lectures are actually like on pen and paper or on blackboard. I thought it would be easy to understand. As I always used to mention, I am not a mathematician, but I could learn a bit of mathematical morphology, could show some applications. It is easier for others, engineers and the core applied mathematicians. They can really do wonders. But particularly young generation, I know that Professor Salim Afsa is there, and he is very familiar with morphology in in remote sensing. I have seen several of his works.
Hocam, hi.
Hi.
Nice surprise.
It's a surprise. Yes. Yes. You all work together?
Not really.
He is in another university, right?
Yes.
Yeah, different city actually.
Yeah, yeah. I know you have several papers using morphology.
Yeah, I like morphology. My PhD advisor was working on that, so that's how I started. But I also did some other things myself. Yeah, I like morphology. I like the math. I like the ideas.
Have you ever met Jean Serra?
No, just know him by name only.
Yeah, he's a great friend of mine, and So he came here, spent 15 days in India.
Okay.
That was his first ever trip to India, and because he thought that traveling to India was unsafe, but he traveled in 2010 after I joined here. Yes, and Jean Serra, the way he explains, he's a mathematician, but I know how to apply, but I cannot really prove the morphological theory. Particularly lattice theory is too difficult to understand for me.
Okay.
Any other questions from the audience?
I do actually have a question, especially applying the morphological profiles or extended profiles to the image classification problem. We know that there are lots of parameters. So by setting these parameters, like you mentioned that we would have, for example, flat structural element or non-flat structural element. So each of those things would, produce different feature to us. So is there any way, before implementing those methods to a specific problem, in our case, the classification problem, we don't know which parameter is the best for our, output. So is there any intelligent way to set the parameters, or for example, in terms of especially the structural elements? So which one do you think is the best for image classification problem, the non-flat or the flat structural element?
Yeah, so we could see particularly in interpolation, and there was an argument that a flat structuring element should not be used in a actually interpolation problem. And that was argued by actually Jean Serra's student only. And his name is forgotten, and he works in Poland. And I think he was also the reviewer, but we have shown even flat structuring elements work fine when we take infima and suprema between two functions. And if suprema doesn't cross the infima of these two functions, and there is no way I can compute the distance, and they have to crisscross. And if you permit me, and I can show it on board, if you have time, I'll just show it on board. Typically, these are the two functions, and this is f, and let us say this is g. This is g. And in between, there is actually the infima is a pointwise minimum. This is the infima. This is the infima. And this is the suprema. When we actually see them crisscrossing and computing the median line is, this is the interpolation. But sometimes we see that these are actually 1D cases I'm showing. But so between these two, the infima is this and suprema is this, and when I do the dilations on this, and it gets saturated here, it cannot, there is no way that it crosses that. And when I do erosions, and it would, because they say when it doesn't crisscross and the distance is infinite distance, but under such circumstances, you have to use non-flat so that it will actually grow. These values would grow beyond this converging point. So this comes with flat. These two things comes with flat structuring element. Whereas when you use non-flat, actually they grow, and then when it is eroded, and it also comes down to beyond this. And this is where we use a non-flat. And not for every image we have seen this problem, but for a few images when we are trying to compute that rank for pairs, the paired images, we saw that, and then we had to prove, and then there was an argument. But our simulated results have shown with flat structuring element, it has given the best result. But madam, actually, when you are asking that classification problem, I still have all that morphological profiles, extended morphological profiles. which Bendixson group have been arguing and written several papers. So why we should not try with a different structuring element, and how these morphological profiles would change, and how would the classification accuracy it really improves. And these are all open problems, and I think somebody should really take it up. And then the other thing, and which is the best structuring element, which can be adopted, highly adaptive structuring element. I think that is where I think adaptive morphology, somebody should really venture in. And but not many groups are really working on these areas. But I think if some younger groups, if they take, I'm sure that they'll be, or I believe one can really write to Professor Jean Serra. He's very good, and he responds very promptly. Because he knows all of them, and Bendixson and Jocelyn, I think they are all in the same city. And yeah, the Chauncet is one person, because the speed at which they have published, and we could not really catch up with them. So those ideas and those publications, and many they have published, and particularly on hyperspectral images. Even now I have been seeing, and they have very good results.
Thank you very much for your detailed answer.
Okay, it seems we're out of time, but I'm pretty sure Dr. Sagar would be happy to, receive any questions via email when he's available. And you can also check his YouTube lectures, which will be very helpful if you are, interested in these topics. I would like to thank Dr. Sagar once again for these invited lectures, 2 lectures back to back. And this webinar was hosted by GRSS Turkey chapter. And thank you to all participants for participating. And thank you, Dr. Sagar, for your talk.
Thank you so much. And I'm really grateful for this is the first chapter I got the invitation from. Thank you very much.
It's very nice to hear that. Thank
so
you.
If you have recorded, you can share with, I believe they'll put that on YouTube channel. And,
yeah, Leland will put talk on IEEE GRSS YouTube page, so the participants and others can also, check the talk from there.
Sure.
Thank you.
Thank you very much.
Have a good day. Thank you. Bye.